Common questions for correlation tests. What is the strength of the correlation? Next, what is the direction of the relationship? We also included an APA format guide. In this video, we will be performing a correlation test. The question goes, a group of students recorded the number of hours they spent studying and their corresponding exam scores. Your task is to determine whether there is a statistically significant correlation between the two variables. Perform a hypothesis test for correlation at a significance level of 0.05. Clearly state the null and alternative hypothesis. Calculate the Pearson correlation coefficient. The next, based on the critical value and the p-value, indicate whether there is enough evidence to reject the null hypothesis. Next, assess the strength and direction of the relationship between the two variables. And lastly, provide a brief interpretation of the results and discuss what the findings suggest about the relationship between study hours and exam scores in this group of students. We start by opening the app, then click this menu bar and search for correlation test. We will be presented by two boxes where we will input the given datasets. For the X values, we will input the dataset number 1, which is hours spent studying, 10, 8, 12, 15, 7, and 5. Now next, for dataset 2, the Y values, this will be the data for the exam scores, 85, 78, 92, 88, 75, and 60. For the significance level alpha, this is given in the question as 0.05. Next, since there is no clear expectation about the direction of the correlation, and we are just interested in whether there is a significant relationship, a two-tailed test is appropriate. This approach is more conservative as it considers the possibility of a correlation in either direction. Now that we have already provided the required information from us, we can now proceed by clicking Calculate and watching an ad to unlock the solution. The solution starts by summarizing the information that we have provided a while ago. Sample X, which is the dataset number 1, and sample Y, which is dataset number 2, exam scores, significance level alpha, and the type of test. Next, for step 1, we formulate the hypothesis. The null hypothesis states that no linear relationship exists between the two variables, and this is symbolized by a Pearson correlation coefficient that is equal to 0. And the alternative hypothesis states that a linear relationship exists between the two variables, and this is symbolized by a Pearson correlation coefficient that is not equal to 0, meaning it can either be positive or negative. Now we have clearly stated the null and alternative hypothesis. Step number 2, we calculate the degrees of freedom, df. Now to do this, we subtract 2 from the number of data pairs between x and y. Since we have 6 pairs of data, 3, 4, 5, and 6, we subtract 2 from that, giving us a degrees of freedom of 4. For step 3, we now determine the critical value. Now to do this, we use the table of critical values for a Pearson correlation coefficient. This is given in the references below. And here we have the table of critical values. So in this case, we are given the degrees of freedom, which is equal to 4. And we have here the two-tailed significance level alpha of 0.05. So the intersection of this location and this location in the table, which is equal to 0.811, is our critical value. So going back, we have here our critical value is equal to 0.811. We proceed to step 4, state the decision rule. To formulate the decision rule, we will use the critical value approach, which means we compare the calculated correlation coefficient with the critical value. As a result, the decision rule is to reject the null hypothesis if the sample correlation coefficient is greater than the absolute value of 0.811. Otherwise, fail to reject HO. Now you may be wondering why we use the absolute value symbol in our decision rule. Now, as what we have stated a while ago, we do not know whether the correlation will be positive or negative. That was our premise of conducting a two-tailed test. The critical value for this particular test, negative 0.811 and positive 0.811. Any value that is less than negative 0.811 and any value that is higher than positive 0.811 are considered significant. To make the decision rule brief and concise, we use the absolute value symbol. We now proceed with step number 5, calculate the test statistic. To do this, we will be following a procedure starting with the calculation of the means of each dataset. Here we add each of the individual data points in each dataset and divide it by the sample size. This gives us 9.5 and 79.67. Next, we calculate the standard deviations of each dataset. Next, we calculate the standard deviations of each dataset. Basically, we subtract the sample mean to each individual data point and then square the differences. And then add everything divided by the sample size minus 1. Okay, we take the square root of the result, giving us 3.6194. So here is the complete equation. So for the standard deviation for sample X, for the data set number 1, we have 3.6194. For sample Y, we have 11.5007. Next, we calculate the covariance between the two data sets. To do this, we calculate the deviations from the mean. We do this by subtracting the mean of the dataset to each data point in that dataset. So for each data point in X, we subtract 9.5. So here we have 10, we have 8, we have 12, 15, 7, and 5. And then for each data point in Y, we subtract the mean of 79.67. So here we have 85, then 78, then 92, okay, 88, 75, and 60. The products are summed up, resulting in the sum of the product deviations. And finally, okay, we divide by sample size minus 1 to obtain the covariance. So the result will be 36.4. We are now ready to calculate the sample correlation coefficient R, which is the quotient of the covariance between X and Y divided by the product of the standard deviations. And so we get the value of 0.8745. Now we already have the Pearson correlation coefficient. For step 6, we formulate the conclusion using our decision rule. So since the absolute value of the correlation coefficient 0.8745 is greater than the critical value of 0.811, the result of the test is statistically significant. We reject the null hypothesis, stating that there is no relationship between the two variables. We have sufficient evidence to show that there is a significant linear relationship between the two variables. In addition, the p-value for the correlation coefficient is 0.0227. Since this is less than the significance level, this indicates that the correlation is statistically significant. The result of the p-value approach and the critical value approach are just the same. They are both statistically significant. In other words, we have already used the critical value and the p-value to indicate whether there is enough evidence to reject the null hypothesis. We also included an APA format guide. So a person's correlation coefficient was computed to assess the relationship between the number of hours spent studying and the corresponding exam score. The analysis revealed a statistically significant correlation with the sample correlation coefficient with 4 degrees of freedom equal to 0.8745, which is a p-value that is less than 0.05, indicating a positive association between the two variables. The result suggests that an increase in the number of hours spent studying are associated with an increase in the exam score. This finding is robust and unlikely due to random chance. We have provided a brief interpretation of the results and discussed what the findings suggest about the relationship between study hours and exam scores in this group of students. Common questions for correlation tests. What is the strength of the correlation? The strength of the correlation is categorized as follows. If the absolute value of the sample correlation coefficient is between 0 and zero point 0.3, the correlation is considered weak. Next, if it is between zero point 0.3 and zero point 0.7, the correlation is considered moderate. And lastly, if it is between zero point 0.7 and 1, the correlation is considered strong. Now, since the correlation coefficient that we have calculated a while ago has an absolute value of 0.8745, the linear relationship between the number of hours spent studying and the corresponding exam scores is considered strong, since its value is greater than zero point 0.7. Next, what is the direction of the relationship? Now, this can be easily answered by looking at the sign of the correlation coefficient, whether it's positive or negative. In addition, we can visualize the direction of the relationship by creating a scatter plot, where each pair of data is represented as points on the coordinate system. This is shown in the following graph. If an increase in the value of x, which is the number of hours spent studying, results in an increase in the value of y, which is the corresponding exam scores, we have a positive linear relationship. On the contrary, if an increase in the value of the number of hours spent studying results in decreases in value of y, then we have a negative linear relationship. As a result, considering the value of the correlation coefficient is positive 0.8745, this indicates that there is a positive linear relationship between the two variables. In other words, when the number of hours spent studying increases, the corresponding exam score also increases. Conversely, when the number of hours spent studying decreases, the corresponding exam scores also decreases. In other words, we have already assessed the strength and direction of the relationship between the two variables. Combining the results of significance, strength of relationship, and the direction of the relationship, we have there is a significantly strong, positive, linear relationship between the number of hours spent studying and exam scores. And that concludes this solution. If you find this video helpful, please leave it a thumbs up. Subscribe to this channel if you're not yet subscribed, and ring the notification bell so that you will be updated on our latest uploads. And as always, I'll see you on the next one.